Here are two solved gas law problems based on Avogadro's principle and Graham's law. Avogadro's principle is based on the idea that since gases are mostly just huge amounts of empty space, the identity of the gas is not that important. If you have a mole of any ideal gas at fixed temperature, which we have chosen to be standard temperature and pressure of 273 Kelvin and 1 atmosphere, which is freezing actually, you will have 22.4 liters of a gas. A mole of any gas at STP is 22.4 liters. We can use this to solve some surprising problems. For instance, what's the density of carbon dioxide gas in grams per liter, STP? Well, we need grams per liter, and it does say STP, helping you to identify this as an Avogadro's principle. And the way I think that's best to solve these is by unit conversion. Know that 22.4 liters is a mole, so we need liters on the bottom. And there it is, 20.4 liters is a mole. And since it's carbon dioxide, recognize that a mole of that is 44 grams. We then just simply have it set up so that moles cancels. We get grams per liter. 44 divided by 22.4 gives us the density of that gas. Hopefully you can realize that's powerful. We can get the density of any gas at standard temperature and pressure. Just use its molar mass and the 22.4 liter relationship, and you're in. Here's a solved Graham's law principle. Don't forget that this is all about the idea that a small gas will travel faster than a large gas, but not that much faster. Technically, we call this the rate of diffusion. You sometimes see it listed as effusion. So if we're comparing the rates of helium and carbon dioxide, all we have to do is write the molar masses, but sometimes you can get confused about which one to put on top or which one to put on the bottom. I recommend you always put the little guy on top. Why? When you flip them over, you'll get a number greater than 1, which makes it far easier to explain what you just calculated. That's what we're doing here. And notice that you have to flip them over. After all, it's an inverse relationship. The larger the molar mass, the slower the rate of diffusion. So we flip them over. And we get 3.3. Notice we have not answered the question. Students oftentimes stop there and move on. But have we really compared the rates? I think you really have not until you put it in the form of a sentence. And what we've determined is that helium diffuses 3.3 times as fast as carbon dioxide. For every 100 yards that the helium diffuses, we will only go 33 yards for roughly, something like that, very close to that for the carbon dioxide. And now you've answered the question.